Water can act as both an acid and a base, which means that when we have a sample of water, it can interact with each other a little bit, and we get what is called the autoionization of water. So, in a sample of water, water can be both a proton donor and a proton acceptor. So two water molecules bumping into each other can actually react and give us a hydronium ion and a hydroxide ion. Okay? And so we get something that looks like that. Now, this is not something that happens super large amounts, but it happens just a little bit. And so I have this double-sided arrow here. Okay, what that means is that this reaction is at what is called equilibrium, meaning that my two water molecules can hit each other and form my hydronium and my hydroxide. That's the forward direction. Well, my hydronium and my hydroxide can collide and go back in the other direction and make back two more waters. So this reaction is reversible. Now, at equilibrium, the rate at which we're going the forward direction equals the rate at which we're going in the reverse direction. Okay? It doesn't mean that the concentrations of everything are the same, but it means that the rate of one direction is equal to the rate of the other direction. Now, various different equilibria are going to favor one side or the other. This particular equilibria favors the reactant side. It favors the water. It doesn't form a whole lot of that hydronium and hydroxide. But once we have something that's at equilibrium, we get what's called an equilibrium constant. Now, equilibrium constants are represented by a capital letter K. If we want to differentiate different types of equilibrium constants, we have a little subscript next to them. So for water, our autoionization equilibrium constant is a capital K with a lowercase w next to it. So it looks like this, Kw. Okay? And so we have this equilibrium. And so the important thing here is this right here. Okay? And then we say at 25 degrees Celsius because that's basically room temperature. So we're working at room temperature. And so this allows us to do some calculations because let's say we know the hydronium ion concentration of something. Well, if we know the hydronium concentration and we know Kw, can we figure out hydroxide? Absolutely. Or what if we know hydroxide and we know Kw? We can figure out hydronium. And again, this is a constant. Okay, which means that Kw doesn't change. It means that the ratio of my hydronium to my hydroxide needs to stay the same. So if I increase one, I have to decrease the other. If I increase one, I have to decrease the other. Okay? All right. And so in pure water, we get this interaction here. And I don't know what happened here, but every time I bring this up, I'm losing my negative signs on my equations. Weird. So, pure deionized water, we get hydronium and hydroxide concentrations equal to each other, and that's this 1 times 10 to the negative 7th. And so then our Kw, if I take those concentrations 1 times 10 to the negative 7th times 1 times 10 to the negative 7th, I get 1 times 10 to the negative 14th. Okay? If I change one, I get the inverse change in the other. So if I'm looking at something that's acidic, I'm going to have more hydronium than hydroxide. If I've got something that's basic, I'll have more hydroxide than hydronium. And when it's neutral, they equal each other. Okay? And so there's a visual for you. So acidic, we've got more hydronium. Basic, we have more hydroxide. And neutral, they are equal to each other. Okay? And so I can use that Kw to go between them. All right, so I've got a research chemist who is adding some hydrogen chloride gas to water at 25 degrees Celsius. We've got a solution with a hydronium ion concentration of 3 times 10 to the negative 4th. All right, so we need to figure out what that hydroxide concentration is. So again, we have our Kw is equal to 1.0 times 10 to the negative 14th, okay? And that is equal to now when you see brackets, okay, this is concentration and capital M, that molarity. So those brackets are going to mean we're dealing with concentrations in molarity. So we need to figure out hydroxide. So hydroxide will rearrange, and we'll get our Kw over our hydronium. Okay? All right, so we get 1.0 times 10 to the negative 14th over 3.0 times 10 to the negative 4th. All right, and we're going to get 3.3 times 10 to the negative 10th. Okay? All right, so hydronium was 3.0 times 10 to the negative 4th. Hydroxide, 3.3 times 10 to the negative 10th. So I look at those. Well, 10 to the negative 4th is much larger than 10 to the negative 10th. So my hydronium ion concentration is larger, so this is, I don't know, acidic. Okay, so that is how we can work with that to figure out whether or not we have a solution that's acidic, basic, or neutral.